Hello! In this video, we will look at a neat way to set up a system for calculating pressure losses along a pipeline and extend it so that we can compare different configurations for our design. This setup is also great to have if you just want to quickly find out how much pressure loss you will have over a certain distance with a given flow. So let's jump right into it. We will be using Excel to set up this scheme where we can calculate the pressure losses along a pipeline for different setups of our system. So to do this, we are going to use the Colebrook-White equation to calculate the friction factor. And as we see here, the friction factor F is on both sides of the equation, so we will have to use a tool in Excel in order to handle this problem. The other equation we will be using is the Darcy-Weisbach equation to calculate the pressure losses in the pipes. And then we have the possibility to include the minor losses, to include the K factor for the type of component we have that causes the minor loss. And then we use the velocity squared over 2g. And then the number of elements if you have a certain number of 90-degree bends, for example. So the way this is set up is that we have path A and path B, or it could just be scenario A and scenario B, where we compare different setups. So we have the flow here in liters per second, we have the length, we have the inner diameter, we have the density of water, the G, the K for the roughness, the small k, which I have denoted it here. So the roughness of the pipe. And then we have the dynamic viscosity. And then we just, in order to do the computations, we make the flow to be in cubic per seconds, and then the area to be in square meters. We use the dimension, of course, do the calculation. And then we compute the velocity by taking the flow and divide it by the area. And then we have this section where we calculate the Reynolds number. And when we have that, we have this cell that calculates. And when we have that, we have this cell for the Colebrook friction factor F, which is here. And here is the part that Excel comes into play, because we can use a neat function that allows us to compute the friction factor. So I have just referenced this cell, which is the Colebrook. This is in Norwegian. It should be Colebrook computation for path A in this example. And it's conversely the same for this one, just another path or another scenario that you're investigating. So this cell references this one. And as we see in the Colebrook-White equation, we have a left side and a right side. And I compute the left side in this cell, and I compute the right side of the equation in this cell. And since when we look at the equation, we see that the left side equals the right side. So the difference of the left side and the right side should be 0. Therefore, I have included this cell, which is the difference between those. And in this case, we can see that it is minus 0.52, and that is far from 0, relatively in this context. So what we will be using is the what-if analysis. This is in Norwegian, but in English, it's called what-if analysis. And when we click on this, we will be using this, which is called goal seeking in English. So the way this works is that you put the cell that you want to do something with. You want to change. You want to do a maximize or minimize, or you want to do something with it. So I'm going to choose this one. And here I can say, to what value do you want to set this cell? So I want to have it to be 0, because that's what my problem is to solve. So this cell is set to 0 by changing what cell? This is this one. What cell do you want to change in order to achieve the value of 0 here? And that is, of course, the friction factor. So I'm going to click on this one, the friction factor. And when I click OK, it will do the computation and try to get as close to 0 by changing the friction factor here. So you can see it gave me a summary here, but we can see that now it's minus 0.000256. Yeah, that's the difference between the left side of the equation and the right side of the equation. And the friction factor is this. And I have only here referenced this value. So when you do the goal seek in this area, you will automatically get the Colebrook friction factor here. And then it's just using the Darcy-Weisbach equation to calculate the pressure losses in the pipes based on the length we have here. And if, as I said, if you want to include minor losses, you can do this here. Just put in the K factor, do the computation with the K factor times the velocity squared over 2g. And if you have several components of the same, you can add it here. If you, for example, have 2 rounded inlets in your system or something, and then you get the total pressure loss here. But since I haven't included minor losses here, the total pressure loss will be equal to the pressure losses in the pipe. So I think this is a very nice thing to have. And also if you want to check something really quickly, you're maybe modeling the system in a modeling software and you want to do some hand calculations to just be confident in your results, you can use this setup. And also if you want to compare, what if we have the same flow, the same length. Here we see that the inner diameter is 150, but we want to see what is the pressure losses if we have an inner diameter of 250. Then I have to see that, oh, the friction factor isn't updated. We're far from 0 here. So I will do the goal seeking again. Goal seek. Yeah, it's here. I just gonna do it again, so for completeness sake. We click this cell. This is the one we want to have to be 0 or as close to 0 as we can by changing the friction factor here. And when I click OK, it will do the computation. And here we get minus 0.00037. So it's pretty close to 0. We get the updated here. Oh, this one is not updated. Oh, that was good to know. So this one isn't updated. I tried to do it before I used this scheme here. So what I need to do is to reference this cell, because this area here is what computes the friction factor, and I just want to reference that value. So we can see when we have an inner diameter of 150, we get a pressure loss over a distance of a pipeline length of 1,000 meters. We get 35.36 meters of pressure loss. But if we increase the diameter, everything is the same, but we increase the diameter to 250 millimeters. That's the diameter of the pipeline in path B, this scenario. Then we can see that the pressure losses in the pipe is 2.84. So it's a very big difference between the two setups here. So the diameter has a lot to say when it comes to the pressure loss the pipes experience. So I'm going to leave it at this. So this is, I found this very useful and I've used it in many different settings. So, and of course we can extend it if you want to have path C or scenario C, D, you just copy it and extend it to the right and include this setup. So I hope you guys found it useful. If you have any thoughts or thoughts about this, just leave a comment and we can start a discussion. Or if you have a different approach to dealing with this type of calculations, I would be glad to hear from you. So that's it for this video. I'll see you in a different one. Have a good day and take care.